Hi everybody, welcome to Soft Earth Chalk Talk 5. Today's title is Earth is Resilient. So last week we talked about Earth is fragile, and I gave you an idea about what fragility means in the sense of material science, and basically the upshot is that things don't stay how you put them, right? So a lot of the earth materials that we deal with are sort of reconfiguring themselves, which changes their structure, but also changes their mechanical properties even if they're minimally disturbed. And then under disturbance, they change them even more. And so in some regard, then that means the materials are fragile because they just don't stay in their present state. But we talked a little bit in lecture 2 when we talked about how, everything is threshold and threshold is everything. This idea that a lot of systems on the Earth's surface are actually perched at the critical point and at the threshold, say, between flowing and not flowing. And in that lecture, I already kind of hinted that this introduces both a certain amount of unpredictability and instability because these systems flicker between like flowing and quasi-static states unpredictably. But that also I hinted that it confers a kind of resilience in that no matter how you try to drive these systems, they will bring themselves back to this critical point. And the resilience there doesn't mean that the system is behaving in a way that you want, but it means that the state of behavior of the system is pretty robust. That even if you kick it and shake it, that it will kind of stay in its place, perched at that critical point. So today we're going to talk about the flip side of fragility and resilience in that kind of way. And last week we went a little bit long. Last week was also sunny. Everyone wanted to go outside. Today is kind of rainy and cold, and everyone's moving a little bit slow. Today's going to be shorter and slower. We don't have as much material to cover, so we can take our time. We can settle into some of these concepts. So where I'm going to start is by asking the question, where on Earth is ice? And the diagram that I have here is our usual phase diagram for water that you might be a little tired seeing now, right? But the idea is that, we draw this phase diagram. Here we are. We have our solid and our liquid and our gas, and we know where ice lives in this phase diagram. If you ask this question, where does ice live on planet Earth? Meaning under natural conditions, not under forced conditions in our lab, but out there in the world. Well, we now have to consider the bounds of temperature and pressure that Earth has, right? So we can use this phase diagram, of course, to inform us about that, right? So let's say that the coldest temperatures that we typically see on Earth are -40 or -50 degrees Celsius, something like that, right? And let's say that the warmest temperatures that we experience are somewhere in the hundreds of degrees Celsius at certain hot places on Earth, and maybe closer to 100 in the lived experience, right? And so that puts you like somewhere here. And then in terms of pressure, well, we know that there's atmospheric pressure, but you can go to the bottom of the ocean and the pressures get higher, and we have weird icy things down there under high pressure. We know that you can go to the top of a mountain, the pressure's lower. So there's a range of pressures on Earth too, but that range of pressures is smaller. And if you ask the question then, where does ice live on Earth, right? The regime of the water phase diagram that ice exists in when you factor in the range of temperatures and pressures on Earth is somewhere in there, right? So the idea then is that if you think of the range of temperatures and the range of pressures on Earth, and you think about this phase diagram, that you could use this phase diagram and search planet Earth and say, I expect that places on planet Earth that have the right temperature and pressure ranges are places where I will find ice. So then you can ask the questions like, what controls temperature? I mean, there are obviously localized things like volcanoes and stuff, but in general, if we're thinking at the planetary scale, it's latitude and altitude, right? So you go further toward the poles, on average, things get colder. You go higher up in elevation, the air gets thinner. On average, things get colder. If we think about pressure variations, you would say that it's either altitude, if we're talking about subaerial things above the ocean surface, or you could say depth in the ocean, right? If we're thinking about, you know, the hydrostatic burden. Okay, so indeed, right, we can anticipate just at a global scale where we're going to find ice based on this phase diagram. But the thing I want you to understand is that this phase diagram is like an equilibrium kind of diagram, and it doesn't, it implies maybe that if I find ice here, that I would make a block of ice in that condition, and that block of ice would sit there. And the same molecules would sit there in the same block of ice, right? And if it's stable in this regard, then the molecules will stay in place and the block of ice will just sit there. That is not true, right? I want you to, first thing that we need to understand is that on planet Earth, when we talk about ice, we're talking about a dynamic stability. That even in places where ice persists, it is stable in the sense that there's always ice there. It is not the same ice molecules, right? That there is melting and sublimation and freezing and addition that are all happening together. And it's only in a like population balance kind of perspective that it's stable, right? So as an example, think of a situation. So, you know, we will draw a glacier, right? So here's bedrock right here. We imagine that we're drawing the profile of a glacier, and the glacier is coming down toward the ocean. The glacier comes down, does this, and out here is the open ocean, right? Free surface here. And this right here is ice, and it's flowing this way, right? So we've already hinted a little bit. We talked a little about ice before. This ice, by the way, is both slipping at the boundary over the rock or sediment that's underneath, and it is also deforming internally, right? So it's slow, it's creeping, but there's a slow creeping deformation, and the velocity is being extinguished with depth as the pressure increases. And so the thing about this glacier is that there is mass that's coming in, right? So mass is going to be added typically in the high elevation places far away from the ocean, say, where it's colder, right? And in this situation, what is mass being added to the glacier? It's snow, right? You can see I'm great at drawing snow. So we're adding mass in some places, right? And when you add mass to this glacier, in fact, the addition and thickening of the glacier is actually what causes the glacier to flow. So it's flowing from the place where it has mass added and is thickening to a place where it's thinning, right? So you have sources of mass in the glacier. The glacier is then flowing away from that place where the mass is being added. And where it's reaching the ocean, so first of all, it cracks, right? Remember Plato's cube. There's pieces that are breaking off the front, and those pieces that break off the front make icebergs that eventually flow and melt away. And so that's a mass loss. The other thing that's happening is just sublimation. So there's a little bit of direct mass loss of the solid ice going directly to the atmosphere. And then, of course, there's also melting. And in the melting situation, I'll try to draw this with some perspective view now, which is always a little dangerous, right? But in the melting scenario now, you have meltwater channels, right, that essentially accumulate water and widen until they discharge to the sea, right? So when we find places, like think about Antarctica or the Greenland ice sheet or something like this, in the center of Greenland or in the center of Antarctica, far away from the ocean, these are cold places where snow is added and it stays there. But these glaciers are also flowing toward the ocean where they are losing mass continuously, right? And so this glacier is continuously being created and destroyed. And it's essentially like, you know, you can't step in the same river twice. You can't actually step on the same glacier twice either, right? It's just slower. This is water moving. It's just in its solid form, right? And so the glacier is like a river, and it persists stably as a system, but there's no part in it that is persistent, right? And so that's probably pretty obvious to people, but I just want us to understand that there's a dynamism to these places. And in some sense, that dynamism itself is telling you something about system resilience. What I mean is that you would look at the places where we find glaciers on Earth and you'd say that on average they live in the place where ice is stable. But what you realize is that this stability is very dynamic and even violent, right? That there's just parts where the ice is being mechanically shattered and lost, and there's places where it's bleeding, where the glacier is bleeding out by making these channels. And there's places where we're always losing ice just by direct sublimation. And yet the glacier can persist in its size, right? And so there's a certain resilience to this thing because it's undergoing all this dynamism and even all this violence. And nevertheless, though, there's an addition that balances the subtraction, right? And so this is true when I talk about now all of the stable systems in today's lecture. They're all going to be stable only in a dynamic sense and only in a population balance sense. You shouldn't think of it as a single population of ice molecules or soil particles that are sitting there. You should think of it that some are leaving or losing their coherence and some are being added. All right. So now we could ask a question, a similar question about soil. This is a little bit more complicated. So I should be clear about what I mean by soil. The soil scientists say that sand is not soil, and the soil scientists say that the soil on the moon is not soil. And the argument is that, soil is actually a weathered product. That when we talk about soil, we're not talking about like a pile of sand. We're talking about a material that has undergone some physical and chemical transformation and that has had some biological addition to it. I'm not a soil scientist, but what I'll say in practice is where on Earth does soil exist where what everyone would recognize as soil? Meaning the brown particulate stuff, the stuff that has some organic matter in it, right? So you know that if you go to the top of a mountain, if you go above the tree line, you can go to these exposed rocky outcrops, so there's no soil up there, right? The wind is whipping, it's super cold, the slopes are steep, and it's barren rock, right? You also know that you can follow a river down to the beach, and you get to this place where you move out of the swampy, marshy area where there's lots of soil, waterlogged, but soil nonetheless, and you get to the sandy part of the beach where it's just loose grains of sand, and there's no organic matter, there's no like in situ developed weathering and transformation that's developing this nice soil column. And so we kind of understand that there's places where there's brown, organic, rich soil, and there's places where there isn't. And that must say something about the environmental conditions. The flip side that I'm asking this is, where on Earth is soil a stable and resilient material? Okay, so now I'm going to tell you, we do not have phase diagrams for soil like we do for water, right? I mean, there's no first principles derivation. You do soil's not one material. By definition, we're saying, where do we find a complicated material that's made up of a bunch of building blocks put together, right? Whereas when we draw this phase diagram for water, we know that water is a fairly simple material. It's one material, and we know that it makes a crystal, which means that we have equations of state that we can derive this from. You can't do that for soil. So when I'm drawing these diagrams, this is like, I know everything is cartoons, but this is like literally cartoons, okay? These diagrams you can't find anywhere in a textbook, okay? So this is just me guessing. But we'll draw it, since we don't have a phase diagram, it doesn't make sense to talk about things like pressure, right? We could talk about, though, variables that we know vary on planet Earth and that have some control, right? So altitude and temperature. So we do know that in places where it's too cold that we don't develop soil. Basically, if you don't have liquid water available to dissolve stuff, cause reactions, to facilitate life, then you don't really have the development of soils, right? And so there's some line here. It's not exactly freezing, but let's just say roughly associated with something like freezing, where below that you're just not going to see soil develop, okay? There's also, this one is a little harder to delineate, but altitude itself is a kind of independent control. Now the problem is that on Earth, altitude and temperature do not vary independently, they co-vary, right? But we know that there are places where above certain altitudes, we just never find soil. You know, that could be related to the steepness of the slopes on very high mountaintops, right? It could be related to the rates of erosion and things like this that are associated with these very high elevations and steep slopes. So altitude is some kind of indirect control, right, on the presence of soil. But above certain altitudes, you don't get it. So it means that there's no soil over here and there's no soil up here. And so if you wanted to think about it, you might imagine then that there's like a line that looks something like this. Right? Where, you know, as long as it's warm enough, I can basically have soil. There's this thing where as the temperature goes up, there's an increasing tolerance of altitudes where I could have soil, but then at some point there's a hard limit where I won't get any above there, okay? But this is made up, but I'm just trying to give you an idea of thinking about soil as a material and its distribution on planet Earth in the same way that we might think about ice. Of course, another important control is temperature. And temperature is really important because of its control on chemical reactions and on microorganisms and other things that live in soil that also indirectly are related to rates of chemical reactions, right? So for all kinds of reasons, temperature is, or precipitation is an important, for all kinds of reasons, precipitation is an important variable, right? So I could do precipitation against temperature or precipitation against altitude. I'll just make it precipitation against altitude. So similarly, there's a minimum level of precipitation below which we don't see soil development. If you go to the desert, you can see sand and a little bit of silt compacted down, but you don't see developed soil profiles, right? So we know that in places that are super dry, that we just kind of preserve granular material and that we don't generate organic matter, we don't precipitate clay, we don't do the things that make complex soils, right? So for sure, we have a certain amount of precipitation below which we don't get it. We've already talked about the altitude control, that above a certain altitude, we're not going to get it. And so then you might imagine if you were going to try to draw some, like, you know, some diagram for here, maybe it looks something like this, right? That there's a regime where soil can live. So maybe the better way to think about this is to actually like illustrate it on a mountain, right? So let's imagine that we have a mountain, right? So we're gonna draw a mountain here. Better late than never, Paulo. Thank you. So we're gonna draw the mountain here, right? And we'll say that this mountain, I'll draw these cracks in here to demonstrate to you that all of these places where these cracks are, this is solid rock, right? And then on top of that, we have developed a layer of soil, right? And so the mountain is there at its slope, and then there's a layer of soil at a gentler slope, right? And in order to make it clear that this is all soil, I'm also going to draw some nice little happy trees, right? Now you can tell it's a mountain, right? Smell the ponderosa pines, right? Yeah, you love it. So, you know, when you think about it, right, up here in the really high elevations, we know that the temperature is low. Up here, we know that it's snowing. Down here in the lower elevations where it's warmer, we're delivering precipitation as rain, right? And so when you draw this mountain, you can see the gradient in temperature and in precipitation, and you can imagine the way that it plays out. So with this mountain range, the important thing is that the mountain is going up. Remember we talked about plate tectonics and the collisions of particles, or the collisions of continents, right? So the mountain is uplifting. Anywhere where there's a mountain, right? We'll talk about these steep mountains. They're uplifting, okay? And then, of course, as the mountain uplifts, it gets steep. and it causes erosion. And this system has a steady state, right? So we talked about the steady state with the glacier. The steady state is that we're adding mass from snow, right? And that we're losing mass by melting and by fragmentation, right? In the case of the mountain range, right, when we think about this mountain, we are adding mass to it by uplifting, right? So it's actually the collision of tectonic plates underneath, which is adding mass. That's a source term. And the sink term here is that we are breaking this rock material, dissolving it and breaking it down into particles. Remember, we talked about that in lecture 3. And those particles are being transported down by erosion. And so the steady state situation for this mountain range is where the uplift rate is equal to the erosion rate. So uplift, you can think of pushing up, it's a source term. Erosion is a sink term. And this system can be being driven strongly. And the steady state that it will find is the steady state where uplift balances erosion. There's a lot of things that need to happen in order for that balance to happen, right? Because tectonics is pushing the plates up, but then the rock needs to be turned into soil, and then the soil needs to be transported downslope, and that happens by gravity, by dissolution, by overland flow and transport, by creep, by landsliding, right? And so understand that this balance right here, it does indeed happen, but this balance is a balance that is accomplished only on like million-year timescales, and only on spatial scales averaging over like 1,000 kilometers, right? There is nowhere locally on the landscape where this is balanced, right? It is only balanced in the limit of infinity. Number of particles goes to infinity. Time goes to being really large, right? But there is a steady state situation here. So if we wanted to think about that a little bit more physically, I would say, okay, look. Let's think about this kind of like we did with the de Morgan number. We're going to think about this for creating and sustaining soil. We'll say, look, there's some time scale that it takes to weather rock, to take bare, fractured up rock and break it down and develop soil. That's a whole field of soil science wrapped up in my time scale of weathering, right? But we'll say that there's some time scale that it takes to weather rocks, which is related to the material the rock is made of, how susceptible it is to being broken apart, and is also related to the environment, how much water, what the temperature is, all those kind of things, okay? And then we would say that we're going to compare that time scale. We're going to compare that time scale to a time scale of erosion. So this is a time, the top time scale is the time it takes to make the soil, and the bottom time scale is the time it takes to remove the soil and strip it away. And if this time scale is a lot bigger than 1, it takes a long time to weather rock into soil, and it compared to the time it takes to just move those particles down the slope, those are the places where you're not going to find soil, right? It doesn't mean that you can't ever make soil there, but it means the moment you make it, it just gets stripped away, right? So you could either have very fast rates of erosion or very slow rates of weathering, and they would have the same effect, that you're not going to have soil, right? And the alternative, obviously, if you have a weathering timescale over an erosion timescale, and let's just say that it's big, so erosion is slow, weathering is relatively fast, you can build very, very thick blankets of soil, right? And you might have to dig tens of meters down to find bedrock, right? So when you think about this in the context of this mountain profile, right? This point right here, this is the limiting point where the erosion timescale balances the weathering timescale. And as you go down slope and you see the soil profile thickening, it means that the rate of erosion is decreasing relative to the rate of weathering. And actually, they're both happening. The erosion rate is highest in the steepest part of the mountain, and the weathering is the lowest because it's cold and there's not much water. As you accumulate water and temperature increases going down, the weathering timescale gets faster and the erosion timescale gets slower, right? And so you now have the situation of moving from no soil to a lot of soil moving down the mountain. All right. So You know, this weathering thing I said is a function of, let's just draw it out. It's a function of precipitation and temperature primarily. This erosion rate, at least if we're balancing over like million-year timescales, the erosion rate is basically a function of tectonics, right? Because it's ultimately related to the uplift rate, and the uplift rate is driven by tectonics, all right? So this is all just in terms of these timescales. Maybe we want to think about this a little bit more in terms of stresses. So we think about the soil on the mountain, and we know that, you know, there's heating and cooling that's happening, right? That's one kind of stress. We know that there's precipitation. We talked about the precipitation a little bit before. Precipitation changes the stress state of soil when the soil fills up with water, right? Precipitation changes the stress state in terms of capillarity or stickiness between the particles. Precipitation can have some other effects too. We also know, right? So we have earthquakes and shaking that's acting on the soil. And then sometimes directly, the wind. Oftentimes indirectly, changes in atmospheric pressure. You might not think about it, but it turns out that changes in atmospheric pressure, you can measure that there's a response in the soil. The creep rate of the soil changes when the atmospheric pressure changes, okay? So all of these things are stresses that are acting on the soil, and all of these things are also acting to determine whether or not that soil can persist. And what I want to point out then is that for sure, to have soil existing and persisting in some part of the landscape, you need to have a weathering rate that is fast enough compared to erosion. But what you also need is that the soil can withstand these stresses, right? What I mean is the stresses that are driving the soil to move, that are shaking it, that are cooking it, that are trying to dissolve it, right? That are squeezing it together and eroding it and picking it up and transporting it. When you walk outside and you see soil there, you should never take for granted that that soil is a miraculous product. That soil is material, and that soil is telling you that that material is capable of withstanding all of these stresses, right? If it were not capable of withstanding all of those stresses and persisting, it wouldn't be there. Remember, that does not mean that the individual grains are all stable. It's just like we said with the glacier, right? There is rock underneath the soil that is being converted and broken apart and turned into grains. And there is soil on the top that is getting stripped and eroded away. No individual parcel of soil is stable, but the entire system is dynamically stable. It's a population balance, right? And so I want to go a little bit further now. It's not just that the soil can withstand these stresses. What I want us to think about is that the soil quite literally is an evolved material. It has evolved to have the complex composition that it has precisely because those materials are the ones that form and survive under these stresses, okay? The materials that you see in soil are by definition the ones that persist in this climate. The materials you do not see in that soil are either ones that aren't made here in the first place or can't persist under this humidity, this precipitation, this temperature, and so on. Okay? So in that regard, I'm bringing up this dynamism because I want you to understand, just like we talked about with the glacier, these stresses, it is an onslaught of stresses on the soils that we see outside. They are constantly being shaken, eroded, picked up, and dissolved. And we are also constantly converting more rock into soil. And that those two things are happening in a kind of balance, right? And so I do want you to think about that when I say that these soils are evolved, number one is that they're evolved under this kind of selective pressure from these stresses. What I also mean by that we're going to get into a little bit, is that the soils are also very heterogeneous, right? So this thing that we call soil that I said we only find where it's temperate enough, we only find where it's warm enough or dry, wet enough or whatever. What I want you to understand is that these things that we call soils, they don't just look different like they're brownish. They're actually very different from something that's just like a pile of sand. They have a multitude of components that are actually like a hierarchical network. And so, when you think about an ecosystem and a resilient ecosystem, you know that you have these different organisms that are linked together. When you think about the soil, it is also a hierarchy of different materials that are actually linked together across scales. And that this network is resilient and this network is stable. And so I want to talk about that a little bit. So just to give you an idea about extending this further, about landscapes being resilient in the environments that they're made in. To give you another example, let's think about a sand dune. Okay, so we're looking at a sand dune from above. This is my favorite kind of classic kind of sand dune. It's called a Barkhan dune. You can see them in the desert. What? What's so funny about my Barkhan dune?
I love your sand dune.
Okay, good. I thought you were, yeah, it is like a croissant. And so we're looking at the sand dune from above, right? The wind is blowing from left to right. And if you take a cross section of the sand dune, this is what the cross section looks like, okay? So the wind is blowing from left to right. Just to give you an idea, we're talking sand dunes that are meters high, 100 meters long. As the wind hits these sand dunes, the flow speeds up. As the flow speeds up, what happens is that sand grains that are here, they get picked up and they get bounced across the dune until they find the downwind side, which is shielded from the wind, and there they deposit. And so what that means then is that there's a zone of erosion on the upwind side. There's a zone of deposition on the downwind side. These dunes are on the move, okay? When you see sand dunes in the Sahara or in white sands, my favorite place, these dunes are migrating like a meter per year. In 50 years, they'll move one full wavelength, okay? So they're not stable in the sense that they're sitting in one place, but they are pattern stable in that they will persist in their height and in their wavelength, okay? So in order for them to be pattern stable, what has to happen is that the grains that get eroded on this side, they get caught in this side, okay? Now, what happens if the fluid stress that's blowing on them is much, much greater than the threshold entrainment stress, right? So there's a critical minimum amount of wind stress that you need to pick up a grain. If the wind blows a lot harder than that, what happens? Well, instead of a sand grain bouncing along the surface, the sand grain gets entrained, suspended into the flow, and it gets whisked away. Which means that the grains that get picked up on the upwind side don't get trapped in the downwind side. And when that happens, the dunes disappear, okay? So why am I talking about this in the context of resilience? Basically, whenever you see a sand dune, it is telling you that the strong winds that come along during the windstorms in that environment, the stress associated with those strong winds is just 1 plus epsilon times the threshold stress. What I mean is that the stress during the big wind events is only slightly bigger than the threshold. That slightly bigger is the condition by which sand grains bounce without getting whisked away into the flow. So if The wind is below threshold, you don't get transport at all. The dune just gets vegetated and it dies in place. If the winds are too strong, the sand gets stripped away and the dune gets bled dry of all of its sand. And so when you see sand dunes, they are quite literally telling you that you are in an environment that is near threshold for that sand. Okay? So this thing is migrating, it's eroding, it's depositing, and yet it is pattern stable, right? And so that is an example of this resilience, but it also, by the way, tells you that you can do in reverse, that you can go to a place on Earth or in the solar system, and when you find sand dunes, you can interpret the wind environment that formed them because you know that they're only forming when the winds are very close to threshold for that kind of material, okay? So sand dunes are near threshold. They're not the only thing, right? We talked about this during lecture 2, right? So, right, remember, I'm doing that dangerous thing of drawing a river in perspective and also coming toward us. Here's a meandering river with a channel, right? So we know that we look at the cross-section of this river. We know that it's made of particles. We know that the flow comes down and moves those particles, right? Remember, though, that the stress is just above threshold for the river, too. Remember that if the stress gets too big, the riverbanks get activated, and the river channel widens, and the stress drops, and it brings it back to threshold, right? So we talked about that in lecture 2, that rivers organize themselves to be just above the threshold of motion during the flood events, right? So again now, we know that the river's not static, right? The river is meandering, it's eroding on the outside bend, it's depositing these point bars on the inside bend, it's wiggling and dancing around. But if you average the hell out of it, you will find that there is a stable average width and depth and slope, and those conditions are the conditions associated with the flow being right there in the vicinity of the threshold of motion. So you have a super dynamic system, but with a population balance that is stable, right? And when you try to whack this system, if you increase the peak floods, or you decrease the peak floods, or you change their intensity or duration or something, or how often they come, what you will find is that the river is going to adjust itself so that it is always very close to threshold for whatever the climatic regime is that's there. That's resilience, right? That is a system that pulls itself to the critical point. Remember, it's self-organized critical. The idea there is that you don't have to do anything special to get the system to get to that point, right? Now, the river might have to be a different size or a different shape in order to accommodate that, right? It doesn't mean nothing happens. If we suddenly double the amount of water in a river today, stuff's going to happen. The river's going to have to erode and get wider in order to accommodate, but it's going to relax back to this threshold state. But the width and depth of the river will be different at that new threshold state, right? By the way, not to beat a dead horse, same principle at the beach, okay? So when you go to the beach and you're enjoying the waves crashing on the shore, right? And so, whoops, sorry. This is just the beach in profile, just to give you the idea of the slope. So the waves are coming in, breaking, washing back down, and if you stand there and you watch that at the beach, you see the grains get suspended and kicked up temporarily. And then you see them deposit and get dropped back down when the wave comes, and then they get kicked up again and drop back down. So there's these big fluctuations. But the big fluctuations are fluctuations around nothing happening. The beach adjusts its slope and its grain size so that it is just in the vicinity of the threshold of motion for the wave climate that it experiences. And if you hit it with a more energetic wave climate, it will adjust its slope or its grain size in order to be at threshold there, right? The funny thing about resilience in the beach is that the resilience from the beach's perspective looks like the opposite of resilience to us as people, right? So we think about resilience of the beach environments like down the Jersey Shore and the Barrier Islands, where like, oh, these islands are really fragile, they're not resilient, and we're really worried about them in sea level rise and storms, and the idea is that we think that we need to do things to make the islands more resilient. What we mean really is that we need to do things to make our homes withstand the storms better. The Barrier Islands are perfectly resilient, okay? When sand gets blasted out of one place, it gets deposited in another place, and the whole system is just adjusting its shape so that it's always close to critical. The problem is that we are intolerant of the system adjusting its shape, right? So this system is resilient. When the wave climate changes, the beach changes in order to still have a beach there. But the beach might have to migrate half a kilometer inland to be in that new equilibrium. That's resilience from the perspective of the island. The pattern will persist even when the wave climate changes. But it is not okay for us, because when the island goes over there and our houses are over here, that's bad, right? So understand when I say resilience, I am talking from the perspective of the system maintaining its coherence. I'm not talking about the resilience of our infrastructure that's built on and around it, right? And you're probably starting to get a theme, right? The stability of glaciers, the stability of soil, the stability of landscapes is only a stability in the sense that the system persists. All of these are flowing, all of these are falling apart, and all of them are being built anew, okay? So they're very resilient as a dynamical system. They're just also very dynamic, okay? So this kind of resilience, of course, I want to connect to earth materials that we were talking about a little bit earlier. And of course, humans have been building on and with the landscape for a long time. And we have some ideas about how to take advantage of the resilience of earth materials and actually use that to our advantage. Work with the resilience of natural materials and the dynamism of natural materials rather than working against them, right? The example I just gave you on the beach is an example of us working against the dynamism and resilience of natural earth systems. It's much better when we work with it, right? So there's a classic example of that, right? So let's talk about building with earth materials. So I'm going to do a bad but cute drawing of a little adobe house, okay? You all with me? You can tell? So here, it'll have terracotta on it, if that helps you envision it, right? You sense it, right? Okay. And to try to illustrate to you that it's adobe, I'll even like fill it in a little bit orangey. Okay. So adobe is soil, right? Let's be upfront here. Here's the thing about adobe is that what we do is you take soil, you mix it with a little bit of water, and when you do that, right? So soil plus water, you make a paste, right? And so you can make a material that has a consistency of something like stucco, right? It's something that the engineers call workable, right? Or workability, right? So you mix the water in just right so that it's workable, so that you can mold it into brick-like shapes and things like that, right? But without, without it flowing away on its own, right? So it needs to have a pretty high yield stress that without touching it, it'll sit there, but that you can work it with your hands, right? Okay. So you take the soil plus water and it makes this paste. You lay it out how you want, and then you dry it. Now, there are a few different ways people do this, right? Sometimes you just make a mud hut and you let it dry by the sun, and the whole thing can come together. Other time you make bricks, right? So you make little adobe bricks and then you actually bake them and you drive all the water out, right? But whether you bake them and you drive all the water out and pull it together to make really solid bricks, or you make like a mud hut and you just let it dry to the air, what you're doing is you're taking a paste that's workable and then you're driving the water away from it so that you're pretty much just left with soil in the end, right? So when it's dry, it's a solid. Now, here's the interesting thing, right? Let's say that you get some cracks in your adobe, which is inevitable, right? Among other reasons, because it's sitting on some soil that's creeping, right? And so you get some cracks in here. Well, depending on the material, so some adobe materials are prepared in such a way, if you bake it, you're out of luck. But if you didn't bake your adobe material, it's actually still plastic enough and porous enough. What you can do is you can come back and you can apply some water on here. You can soften it a little bit, and you can massage it, and you can massage away the crack, right? So what you're doing is you're saying, I want to make a material that's strong, but I don't want it to be irreversibly strong like cement. Because if it's irreversibly strong like cement, when it gets a crack, it won't come back together. I want it to be more like the soil on the hillside. I want it to be more like the sand dune. I want it to be that this material stays, but I'm expecting it's going to break in some places, but that I can rearrange it intentionally to fix that breakage, right? And make a material that is resilient. So we know that the oldest structures that we have on planet Earth are made of earth materials, right? There's a resilience to them. There's the fact that there's material that you can continuously harvest from right next to you to add to it, right? And there's a resilience that you can wet it and you can rework it. Now, there's a challenge with this. Humans have not built with adobe everywhere, right? It turns out that you have to have soil that is complex enough, like we talked about earlier, that has some clay and organic matter in it, so that it will have this workability, which means it has to be a little bit wet. It has to be wet enough to have precipitation of clay and growing of plants and stuff like that. However, if it's too wet, your adobe will dissolve and erode away, right? And so right now we have this beautiful, resilient, sustainable material, but it's only sustainable in places that have this Goldilocks of climatic and material conditions, right? Another example that we can draw is dams. Okay? So this is the dam I've drawn here, right? So we'll say this is the reservoir ponded up behind the dam, right? You can see it. And there's this thing where, of course, we build dams, we don't want them to break. Often, when we build dams out of cement. Cement is strong, cement is portable, we can pour it in molds, right? We understand that. It has really well-controlled mechanical properties, but the problem is that if you build dams in places where there is a lot of shaking, like with earthquakes, the problem with cement is that it is brittle, right? So remember our little diagrams here, right? If we look at stress against strain, so when we're thinking about the cement, it has a high yield stress here, but beyond that yield stress, it loses strength catastrophically, right? And so cement is strong but brittle, and if you shake it too hard, it'll withstand that shaking until it doesn't, and the moment that it doesn't, it will catastrophically fall apart. So, in places where there are earthquakes, we build not with cement, but with soil. So all of the tall dams in California are earth dams. They are not made out of cement. A lot of people are surprised by that, especially because it seems really low tech and even dangerous because it's permeable. They're like more porous than cement is. You have to like maintain them all the time. You know, you have to check on them, and there might be leaks that are eroding on the inside that you can't really see and all this kind of stuff. And yet, in places where there's earthquakes, we build with soil instead of building with cement. We actually know that our earthen dams are weaker. We have to use more material in order to build with them. The yield stress is smaller. But what we also know is that they fail much more gradually. So first of all, they have a wide failure envelope, so they might start to fail but not get there. But the other thing, oh, I erased, oh, here we are, is that they can be self-healing. So there are actually earth dams that we build now where we prepare the soil in such a way that when it gets shaken, that it will settle and the grains will relocate, right? They will accommodate the strain from the shaking of the earthquake by deforming internally. And remember that when you have a soft, complex material in amorphous solid that deforms internally, it's distributed, right? You like, I did that with my hands. You can tell I mean distributed. What I mean is that instead of a crack propagating through the material, you have a bunch of different places where the grains shuffle around, okay? So, I want to get a little bit into the granular mechanics side of this, at least as mechanical as we're going to get, right? And I want to talk about that by saying, what are the kinds of different materials that combine together in soil to actually make it have the right properties? Okay, so we'll start by thinking of simple sand, which remember we say is not soil. And so you can all tell that's a foot, right? You love it. Okay, so foot pushes down on sand. And what we know, right, is that the sand can give a little bit, but eventually this is dry sand. We're not going to sink in very far. It can withstand our weight, right? And what we understand then is that dry sand is hard under a compressive load, right? Or it's strong under a compressive load, right? But you know, if you reach down, I won't draw a hand because it'll only be worse. But if I reach down and I want to pick a grain of sand up, right? So I'm pulling in tension. I understand that there is no resistance to tension, okay? So sand is a purely frictional material. The frictional material is strong under compressive loads, but if I try to pull it apart, there is nothing, if I zoom in here on the sand grains, right? And I want to pull them apart from each other, there's nothing to hold them together. So there's nothing to resist a tensile stress that is applied to sand, right? And so sand alone is a useful material, but it's not a material that we can build a wall with or a house with or anything like that, right? We know that we can't make a sand pile that's any steeper than like 30, 35 degrees, right? Okay. So maybe you see where I'm going. So now let's take sand and we'll add a little water to it, right? So at a large scale, we know that now I can do things like I can build sand castles, right? Now I know that I can build slopes that are 90 degrees, even more than 90 degrees. I know that I could put like a little action figure up here in the top. You know, I could put a little bit of weight on this. But what I know at least is it can withstand its own weight without collapsing, right? And if I zoom in, what's going on here is now the sand grains have liquid bridges between them, right? You can do this experiment simply if you just take two marbles, dip them in water and put them together, right? And then pull the marbles apart. It's not hard to do, but you feel as you pull the marbles apart, you can feel, you see the liquid bridge stretching and you can feel the resistance with your fingers. When we've added water, we haven't just made the sand stronger. We've actually qualitatively changed the mechanical properties of it, because we've now added a resistance to tension when before there was none. So that's a qualitatively new mechanical property that allows us to do qualitatively new things with this, right? So, water's not the only thing that does this. So other things in nature that can add cohesion, right? What we're talking about here, really, when we talk about resistance to tension, that's what I call cohesion. Some people debate about the meaning of cohesion, but to me, cohesion is useful in its distinction from friction just by meaning that it is a resistance to a tensile stress. There's a more technical definitions, but that's what we'll deal with for now. So this is one way, but not the only way to get cohesion in sand. So there are clay particles that are common. I'll just draw a simple clay particle here. Okay, so this is our favorite model mud material in our lab. It's a kaolinite platelet. So I've drawn it like this. This would be 1 or 2 microns in size, right? So a pretty small particle. But what's interesting about clay particles like kaolinite is they have negatively charged faces, but positively charged edges, okay? So there's more face than there is edge. So if you zoom out and you did a point charge approximation, you'd say that clay particle is negatively charged on average, which it is. But now I'll just draw them as little lines. When clay platelets interact with each other, they stick together edge to face and they make aggregates. Now, they're net repulsive, so if the only thing acting on them was the charge, they wouldn't come together. But they also are a couple microns in size. They do settle under gravity in water, albeit slowly. They also get pushed around by stresses. So if gravity or pushing or animals or whatever else push these clay particles into contact with each other, the positives and negatives will find each other, and electrostatically these things will stick together. And so they make these clumpy, sticky aggregates. That electrostatic attraction is a kind of cohesion, right? It adds a resistance to tension. And so if you take modeling clay, right, which you probably all worked with, right? So modeling clay now has this going on, and it has this going on, right? And so you can take the modeling clay and you can mold it, and you realize the consequence of strong cohesion is that you can make arbitrarily complex shapes and they'll hold under their own weight, right? That does not happen with a purely frictional material, right? So if we want to relate this to building, how does that work? Let's say that we want to build a wall and we want it to stand together on its own, right? So we want to use sand. Sand is strong under compression. These clay aggregates are not very strong under compression. If you look at the way I've drawn this, you could squeeze it together and collapse it like a house of cards, right? So sand is strong under compression, but you also want to add clay in all of the pore spaces, which is strong under tension. And what we know from engineering application of this is that there are magic ratios of sand to clay that are basically maximize the contributions of the strengths of each, right? So what you do is you basically add enough sand so that the sand makes the skeleton, so that the sand could hold its own weight. And then you fill in everything around the skeleton with clay, and then you ram it or pack it together, right? So you basically try to eliminate all pore space. And that when you do that, you now build a material that combines the compressive strength of sand with the tensile strength of clay, and you can build a wall. And the wall will hold its own weight, right? And so the techniques that we use to build with now are essentially just optimizing this kind of interaction, but it's building on the techniques that we've already used, that humans discovered experimentally thousands of years ago building with Adobe, right? So we've basically learned how to create the proper mix of materials that will do what Adobe was already doing, okay? Now, thinking about this in the context of landscape stability, right? So we'll now draw again, we're like drawing a hill slope profile. So this right here is the bedrock. Hold on. This right here, that didn't work very well. This right here is the soil. So remember now that what's going on with the soil is all of this complexity, right? You have the sand, you have the clay, you have the sticky stuff, you have the frictional stuff. You also have some water between the pore spaces. And then on top of that, you got plants with roots, right? And essentially, it's like you're taking these sand, clay, water mixtures, and you're now adding networks of fibers. Essentially, what natural soils have is compressive strength from the sand, tensile strength from the clay and water that's there, and then you have this fiber reinforced networks done for free by nature from the plant roots. This fiber reinforcement is actually a technique that we do in cement and other materials when you want to make them strong. And basically the idea is that, let's say that a crack starts to develop in this material, okay? So if the material is made of simple frictional, uniform in size, roughly sand, a crack can shoot right through it. But what happens if you have this hierarchical, complex material with particles and interactions from frictional to cohesive to viscous across scales with this fiber reinforcement, is that a crack tries to grow in one place and that stress gets distributed across a whole bunch of scales and a whole bunch of directions. Essentially, what I'm saying is that soils that are complex, we know that they are ductile. What that means mechanically is that they dissipate cracks, okay? When you have a simple brittle material, one way of saying it is that cracks are self-reinforcing. Cracks are localized. When you have a simple brittle material, the moment a crack starts forming, the stress concentration at the tip just makes the crack rip through the material. When you have a hierarchical complex material, the crack wants to rip through the material, but it just keeps getting sent in a million different directions, okay? And so that is why complex soils that have this ductile response are also more resilient, right? I had mentioned this before. It's worth mentioning again here. If we think about this hillside, we know that the ductile materials, when you have complex soils, that you can have localized failure, what we call landslides, but when the materials are complex, we call them creeping landslides. They actually don't catastrophically rip and fail. It's just kind of like slowly, constantly deforming, right? What we know is that in landscapes where we have simple materials, either geologically it turns out that way, or because there's like a wildfire that removed a bunch of this hierarchical complexity, that you get very large-scale, catastrophic, abrupt landslides, okay? So all of these mechanical differences between brittle and ductile, simple and complex, have applications for understanding and building with more resilient materials, but they also have applications for understanding resilient landscapes, right? Which landscapes can keep getting bombarded but just have slow creeping landslides, and which ones will catastrophically unzip. This is like a large-scale version of this, right? A landslide is like a big-ass crack, right? And a creeping landslide is in a complex material where the crack can't grow and propagate all at once and rip through the material, okay? So the last little bit then this was by request from Shravan. It was in my notes, so you're welcome. Was to connect this point to the energy landscape argument that we talked about last time, right? So, right, when we were looking at simple materials, I gave you this idea of an energy landscape where I said, look, there's one configuration that particles or atoms or things want to align in that will minimize energy. So if they're all jiggling around and you bring down the temperature, you know, strictly or metaphorically, that they're going to settle into some state, right? And so for materials that are crystalline materials, they settle into one particular state. That's the ordered state. And that if you think about yielding with that kind of material, that you can think about it as like tilting the energy landscape, and that the system will stay until you tilt it too much and it will abruptly roll out, right? In case it wasn't obvious, that's this scenario, right? And we had talked about, for the complex materials, that maybe they have an energy landscape like this, right? And so if you bring down the temperature, or remember I had the idea that we had a ship that was sailing around and we're lowering the water, right? Is that you might find yourself trapped here in this configuration. But if you tilt that energy landscape, you tilt until at some point the ball rolls out, but maybe the ball rolls down here, or maybe it skips over that and it rolls down here, right? And what you understand is that if you keep tilting the energy landscape, that you're going to keep getting stuck in these different minima, and you're not just going to flip from one state to another state. That's what's going on here in this curve, right? As you start, you're tilting the energy landscape by increasing the stress. And as you increase the stress, you might jump out of one configuration, but then you get locked in another one, and you keep increasing the stress, but you get locked in another one, and another one, and another one, right? And so this idea that I talked about before of like crystalline materials with simple energy landscapes that have abrupt transitions, those have brittle failure. And the ones that have complex energy landscapes that when you drive the system, that they fail in complicated ways. The relationship then here is to like simple and complex soils, right? And so what we want in terms of landscapes and in terms of building is something like this, right? And it's kind of funny because remember, there's an inherent unpredictability of these systems that are disordered and that undergo continuous rather than abrupt phase transitions, right? We said that like we can't even predict the energy landscape or the range of configuration. So these systems are harder to predict than these systems. But these complex systems are far more resilient to disturbances than these systems are, right? And so the upshot of all of this, in terms of thinking about resilience with earth materials, is this idea. More is different, right? So if you're not familiar, this is a classic 1972 paper by Anderson, which sort of condensed matter physicist that marks basically the beginning of like emergence or complexity science as a field of study within physics, right? But the premise with more is different is, look, when I think about idealized systems and then I start to complexify them, the naive view might be that, well, the system is just more complicated, but it's a more complicated version of the idealized thing. The more is different and emergent idea says, if I take one material like sand, which is frictional, and I take another material like clay, which is sticky, and I add them together, that I can create a material that has emergent physical properties that are unlike the physical properties of either of them, right? And the idea with more is different connecting to this is that the more complex the earth materials are, it's the same thing that we say about ecosystems. Complexity is resilience, right? Complexity is resilience. Redundancy is resilience. Actually having multiple components that are sticky like clay and organic material and water, having multiple populations of frictional particles, right? The idea here is that something happens, some material gets preferentially dissolved or eroded or taken away, and yet the material can still persist. So the idea is that complex earth materials have these emergent mechanical properties. And these emergent mechanical properties result from the multi-scale interactions, from micron-sized clay all the way up to the meter scale of tree roots and things like that, right? This makes them robust and resilient. We also have this idea that these earth materials literally evolve, right? So that we should understand that the resilience of earth materials is telling you that those materials evolve to withstand the range of stresses that are forced upon them by the climate and geological area that they are in. Which means that if we learn how the composition of soil is related to the environment and the climate that we're in, that we can learn some ways we can learn the science of resilience, okay? Remember also that landscapes are close to the threshold stress, right? They're perched at critical. That in and of itself is a kind of resilience, because when you drive these systems away from that critical point, they will adjust a few different knobs until they bring themselves back there. So if you want to work with a landscape, understand that the landscape is resilient to snapping itself back to its threshold state. So working with nature means working with, building and interacting with nature that doesn't fight against the tendency for it to pull itself to the threshold state, right? This resilience, the last part, is this is a dynamic stability, right? All of these systems that we're talking about are population balance things. Particles come in, particles leave. New parts of glacier get created, old parts of glacier get destroyed. Rivers get eroded, rivers deposit, right? So if we learn how complexity emerges in earth materials, right, then we can learn maybe not only to handle the dynamic changes in landscapes, we can also learn to harness them and even build with them with more sustainable geomaterials. So that's where I'll stop for today.
You know, we have all these tools for monitoring landslides and like hill slopes that landslide with some frequency. Do we use the same technology to monitor the failure of earth dams?
Yeah.
Okay.
Yeah. So it's a question about monitoring earth dams. So what I would say that we use a lot of technology in wealthy countries like the US and Europe to monitor the safety of earth dams. So in fact, you know, this is kind of true in a lot of engineered systems, is we usually have more money for them than we have to like monitor natural systems, right? So, but we don't necessarily use the same technologies. So, you know, when we think about monitoring dams, we have like, people will put in strain gauges that are like super high sensitivity and super high resolution. They'll put them in a bunch of places. They'll also be worried about pore pressure inside of the dam, so they'll have a bunch of pressure sensors that are embedded within the dam. There are some landslides that have those things embedded in them, but often very sparsely or not at all, right? On the flip side, when you think about landslides, so, I mean, literally the geometry is turned 90 degrees, right? So the landslide presents a lot of surface area to the sky, and the dam is vertical, right? So with landslides, we tend not to have all these internal monitoring things. We might have a few wells and a few sensors, but not nearly as much as we have in dams. But we can use satellites, right? So landslides that are on big areas on hill slopes, we can use, you know, radar interferometry. We can use repeat aerial photos, and you can see deformation happening on a kilometer scale landslide that's moving downhill. Whereas the cross section that's presented to you on a dam from above is very, very small. So often you can't use those satellite tools to really look at the internal deformation of the dam, because it's just like a big wall. And so then you need to place a bunch of sensors inside of it.